Well, welcome you all to the next video lecture session of Dr. S.J.Sarkar's basic electrical engineering classes. So let us discuss a numerical problem related to three-phase induction motor today. So let us come across the problem. It's given there is a 5 kilowatt 3.3 kV 50 Hz three-phase induction motor which is running at 1440 rpm under full load condition. Now when the motor is unloaded, the rotor speed becomes 1470 rpm. So this is the data which is being given. So what we have to do, we have to find the number of stator poles, no load and full load slip, rotor frequency at the starting, no load and full load, and lastly, if the rotor induced EMF per phase and reactance during standstill condition be 2 kV and 10 ohm respectively, we have to determine the rotor current at the starting, no load condition and full load condition if the rotor resistance is supposed to be 1 ohm. So this data is given to us. So before moving forward, let us just tell you this standstill implies that when the motor is in rest condition, it is not moving. So under that condition, it is called a standstill condition. So let us note down what is given. So it's given the power rating of the motor is 5 kilowatt. The line voltage is 3.3 kV. So mind it, whenever no data is given and it's a three-phase supply, so the voltage value what is given, it is basically the line voltage or 3300 volt. F is 50 hertz. This is given. Another thing is given under full load. The motor speed is 1440 rpm. Speed under no load is 1470 rpm. So this is the data which is given initially. So while taking the last problem, we would be taking that data. So this is given. So the first thing what we need to do, we need to find out the number of stator poles. So what we can see, the speed of the motor is going to vary from 1440 rpm to 1470 rpm. So can we say that this 1470 rpm is the maximum possible speed of the motor? If that is so, we know the relationship. What? F is equal to Pn by 120. Or the very same relationship is given by 120F by P. N is equal to 120F by P. In case of synchronous speed NS, we are doing that one. So we know this relationship. So from that, what we can write, can we write P equal to 120F by N? Now if that is the case, we are not putting the value. So what I had told, this 1470 rpm is the maximum possible speed of the motor. So let us try to find it out. What is this value? So we are putting all the values together. So from that, we are getting this P should be getting 4.08. Now, whether the number of poles can be any float value like this one, it should not be. It should be some integer value. And not only that, it should be an even integer. So what we need to do, we need to round it off to the nearest integer. So this is coming to be 4. So the number of stator poles should be equal to 4. So we had found that one. So this is the first portion what we had solved and we had got the answer. Now coming to the second prospect. We have to find out the no load and full load slip. So to find out that no load and full load slip, we need to find out what is the synchronous speed. So that would be given by 120F by P. So we know P, that is equal to 4, F we know that is 50 Hz. So putting that, we are getting NS is equal to 1500 rpm. So once NS is found, So what we can say, slip under full load will be given by Ns minus Nfl by Ns into 100. This is from the basic definition. Let me not take the 100 right now. Let me take the fractional value. So from the basic definition of slip, we know this is the slip. So putting all the values there, so the full load slip is coming to be 0.04. So this is what? This is the full load slip. So we had found the full load slip. Similarly, no load slip SNL that will be given by Ns minus NL by Ns. So solving that, we are going to find that that value is equal to 0.02. So we have found the full load slip, we have found the no load slip. So we are having this data. Now the first point and second point, it's done. Now coming to the third point. What we need to do, we need to find out the rotor frequency at the starting, no load and full load. So what is the relationship between the rotor frequency and stator frequency? So if you could recall, unlike the transformer, in case of induction motor, the rotor frequency and the supply frequency are not same, but they are related by this relationship, where this Fs is the supply frequency, simply what we can write S into F. So this is the data. So this is the rotor frequency. Now there are three cases. The first case says at starting, when the motor is about to start, what is going to happen? What about NR? NR should be equal to 0. So what it implies? The slip at starting should be equal to Ns minus NR by Ns, so that is coming to be 1. So what is going to happen then? So which imply the rotor frequency during starting will be SST F, that is equal to 50 Hertz. So at the starting, when the motor is about to start, the frequency of the induced EMF or current in the rotor circuit, that would be equal to the supply frequency. So this is what we had found. Now case 2, what is the rotor frequency under no load condition? So under no load condition, what is happening there? The slip under no load is what? 0.02. So what will happen? The rotor frequency under no load condition, that would be SNL into F. So that is equal to basically 1 Hertz. Putting the values and solving it out. And then the other condition is the full load condition. So for full load condition, what is going to happen? SFL is 0.04. So the rotor frequency under this full load condition would be SFL into F. That would be coming to be 2 Hertz. So what we can see, that depending upon the extent of loading, actually the frequency is going to change in case of a induction motor. Which frequency? The rotor frequency is going to change. So if the rotor frequency is going to change, so what is going to happen with the reactance in the rotor? So obviously the rotor reactance is going to change at the standstill condition when the motor is about to start. whatever reactance value is given, that reactance will not remain same when there is a full load condition or there is a no load condition or there is any load condition, because they would have a particular slip, so therefore it is going to change. So now comes the fourth prospect. So in order to understand that phenomena, let us first write the things, and then we would be actually moving towards the equivalent circuit of the induction motor, and we will be referring to that. So what is given to you? It's given that the standstill EMF and since in the rotor that be supposed to be E2 is equal to, it's given 2 kV, so it be 2000 volt, and it is in phase, per phase quantity is given. And what about the reactance? In the rotor, that is given 10 ohm, and what else is given? Rotor resistance, that is R2, is equal to 1 ohm. This data is given to us. Now, let us refer to the equivalent circuit or the rotor equivalent circuit of an induction motor, and we are focusing on the rotor. So what we know, it would be similar to that of a transformer. So it would have a winding, the secondary winding, similar to the secondary winding, we should have a resistance and we should have a reactance there, and then it would be shorted. Why shorted? Because in case of an induction motor, it is generally shorted, in case of a squirrel cage motor directly, or shorted by some resistance. So this is the rotor resistance, this is the reactance. Now, what I had told, the reactance, should understand that phenomena. What we know, the reactance, inductive reactance, that would be equal to J omega L. So that is basically J 2 pi F L. This is what the value is. So we could see that XL is dependent on frequency. Frequency of what? In this case, this should be the rotor. So can we say that this is now becoming J into 2 pi S into Fs into L. So at the standstill condition, slip is equal to 1, and so therefore what is going to happen? Fr is equal to Fs. So this is having some value which is equal to 10 ohm. So what is going to happen? It would now become something like this one. So what we can see, that this reactance in the rotor, that is dependent on slip, and therefore it is not a fixed quantity, it is going to become a variable quantity. It will be a variable reactance, and there would have some induced EMF in the rotor as that of a transformer. Now, what we know, that in case of an induction motor, as the motor catch up the speed, so what is going to happen? The relative speed between the rotor and the rotating magnetic field is going to decrease. So therefore the EMF is going to change. So what is going to happen? That this induced EMF would be a function of slip. So theoretically we are aware of. So this is what the rotor equivalent circuit. And what we have to do, we have to find out what is the rotor current during some conditions. So what we need to do, we need to find out this rotor current, say I2. So this is what is required. So in general, we could write rotor current, which is I2, that will be what? that will be the applied voltage. So what is the applied voltage? S into E2 is the applied voltage. And what is the impedance of the path? That is coming to be R2 plus JSX2. So this is the rotor current. So in that case, this further it can be simplified in this way. I am considering the magnitude of the rotor current only right now. Let me take the magnitude because it would be a vector quantity. So let me taking the magnitude. So it become something like this one. It would be getting something like this one. Now we would be putting the different conditions. So what we need to do, we need to find out the rotor current at starting. So what is going to happen? At starting, we had already discussed that the slip would be equal to 1. So what is going to happen with I2? The relationship would be this one. So all the data are given. So we are simply putting it out and solving it out. We would be getting that this current is equal to 199 ampere. Just check the values. So we are going to get something like this. Then the at no load condition. That is S and L. So under no load condition, the slip is 0.2. So under that case, let it to be starting I2 and L. So that will become what? 0.2 into E2 by root over R2 square plus 0.04 x2 square. This is what is going to happen. We are putting the values together and solving it out. So what we are going to get, that this no load current is coming to be 39.22 ampere. And come to the full load condition. SFL is equal to 0.4. So what is going to happen with I2? FL, that would become 0.4 E2 by root over R2 square plus 0.16 x2 square. This is what it's coming to be. Now if we are going to solve it out, so we can find that that current would be equal to 74 ampere. Roughly we are going to get this data. So from this data, what we can understand, try to understand the analogy. What we know, that basically it is similar to a transformer. So whatever current is drawn by the rotor, in proportion to that, some current would be drawn from the supply through the stator winding. So what is happening? We could see that at the starting, the current drawn by the induction motor is the highest one, not at loaded condition. The starting current of an induction motor is highest. That is true for any induction motor. So we need to limit the starting current so that it can be within some permissible range. So that is why we require starter in case of an induction motor. So since the starting current of an induction motor is the highest value, which is a few times of the rated value. So if you could see 74 and 199, so it's more than 2 times. So in order to limit the starting current, we need to take some action, and that is why starter is required in case of an induction motor. and under no load the current is about 39 ampere, and in the full load the current drawn is 74 ampere. So what we can see, that loading on a motor, when we are applying some mechanical load in the motor, so what is going to happen? The current drawn by the motor is actually going to change. So in electrical system, when we are talking about loading of a motor, it implies that the current drawn by the motor is going to increase. That is what the significance of loading in case of any electrical load. So this is what the point of observation is. So hopefully you could find the thing useful, and if you have any query you can ask it to me afterwards. So I'm stopping here. If still you have some query, you can ask. No issue there. So thank you. Have a nice day.